Okay, so this is the example on page 15. We're asked to write the equilibrium constants for the following cases. Now remember, it's on your formula sheet, and what we're really interested, or make sure we do, is we put the products on top of our reactants. So we've got HI as a product. We do put our states in the brackets, and it's going to be divided by the concentrations of our reactants. And just remember that we also have to include the coefficients now as powers. So your index laws will also be useful. Now, because because we've got concentrations, we also, where we would normally write mole per litre, now we're going to write M, just a capital M for molarity. And oftentimes K doesn't have units, and it won't have in this example because I've got M squared divided by M squared for my units, so they just cancel out. For the second example, remember we've got our products on top, so we've got our lead ions, we've got our chloride ions to the power of 2 divided by the constant, it's going to be divided by 1 because the lead chloride is a solid. So we don't have to even put the divided by 1, we could just leave it as the top like that. But we don't need a value there for our solid. In this case though, and you don't have to include units, that's one of the things that is very clear about the way it's marked, but if you did include the units, hopefully you would know that it should be m cubed. But because when we're multiplying we add the power. And it goes on to tell us that the solubility product of this particular reaction, 1.7 times 10 to the minus 5, that's because this is a small value, it tells us that the lead chloride has low solubility, which is where I was getting myself confused in the last video. All right, and then for this reaction up here, we're then told that we knew what our concentrations were, that the HI is 0.16 molar. And the I2 is 0.030. And the H2 is 0.015. And so that's our calculation. Just remember, we're not writing our multiplication sign. You can put a dot in there if you need to remember, but it's multiplying, not adding. And we end up then with a K value of 56.9. Does this favour the reactants or the products? Products, because our number is greater than 1. All right, we've got another example on page 17. And so let's go through that. We've got 0.0500 mole of sulfur dioxide, 0.0100 moles of oxygen gas, and 0.1500 mole of sulfur trioxide gas. And they're mixed in a 2-litre vessel. and allowed to reach equilibrium according to the equation given. So this is our equation: 2SO2 gas plus O2 gas is in equilibrium with 2SO3 gas, the sulfur trioxide. And analysis showed that 0.1400 mole of sulfur trioxide gas remained in the gas mixture at equilibrium. Determine the equilibrium constant at this temperature. So we're asked, well, what we really need to do is set up an ice table. So remember that the easiest way to do it is to just set this up directly underneath the balanced equation that you've written up top there. But there's a trick in this example, or there's something to note. It's a 2-litre container. And so when we're working out our concentration, we need to keep that in mind, that they are all going to need to be divided by 2.
So for your ice tables, just in general, are you better off to convert them to concentration straight away, or would you, if you're given moles, would you just...
Well, I think you might get confused if you left it as moles. I would convert to concentration straight away, because we know that's how we're going to calculate K. So here, I know it's written out separately, but you can do it in the table, it doesn't matter. We know what we have of the sulfur dioxide. It's 0.0500 moles, but I can just divide that by the volume, and that will tell me my concentration, 0.0250. And we're going to do the same thing for our oxygen, 0.0100 divided by 2. And our sulfur trioxide, now there's an error in the booklet. It should say 0.1500, not 0.05. Divided by 2. That equals 0.0750. And now we've got something that we can start with. So these are our concentrations. If you're not, like, I know it looks a bit messy, but by putting the square brackets around, then that we can see then that they are our concentrations. And we know that after equilibrium has been reached, we know that we had 0.14 moles, 0.1400 divided by 2 is then equal to 0.0700 moles. And so this was initial, and then we've got, I'm going to put out, I might move that down. So I've left room then for the change in the equilibrium. Fit in there. Sorry, I just dropped that down a little bit. So that's what we have at equilibrium. Now we know that the way that we can figure out the changes in concentrations is by working from this one where we know the initial and the final values. And we can see that what has happened here is we have had a reduction That's been our reduction, our change for our sulfur trioxide. And now with looking at this, we go back to our balanced equation, our coefficients, to work out what's happened to the other reactants. So because this is a subtraction, these have to be additions, don't they? Because they are on the other side of the reaction arrow. So they're on this side. So they're going to have to be additions. This one, because we have the two at the front of the sulfur dioxide and the sulfur trioxide, the magnitude will have to be the same. So this one is going up by the same magnitude that the sulfur trioxide went down. And because of the, basically this one has a coefficient of 1, it's going to be half the others. So we're going to be adding 0.0025 to that. Does that make sense? Now we know what we can write then for our final values, and then we'll have our concentrations. So we end up with 0.0075 and 0.0300, and we can calculate K. This is a concentration value for K, and here we've got our product. Don't forget to go back up and look at the balanced equation to put in the correct power. And then we've got 0.0300 squared times 0.0075. And then that gives us 726. And if we were putting in our units, this time it would be m to the minus 1, because we've got m squared divided by m cubed. But, like I said, this is not expected. You don't need to include that. And if you're at all confused by that, you shouldn't write it, because if you write it and it's wrong, then you run the risk of being penalised for it, even though it wasn't expected. So you can, by all means, include it, but just make sure that you understand what you're doing there. Okay? So that's our worked example done.